Hi everyone, I am Paul Tarao and then I will talk today about focusing recursive LLM descents with plans expressed as logic programs. Let me start with an overview. Well, the talk is about how we use logic programs as LLM guides, well, to generate logic programs. Here's the quick overview of what's next. We show how human-designed logic programs guide the systematic exploration of concepts and statements using large language models. And our framework's main components are combined horn clause and dual horn clause logic to verify or falsify theories. We also use recursive LLM descents to extract the LLM's encapsulated knowledge as logic programs. The descent is initiated by a plan expressed as a logic program, and what LLMs do, they will extend this logic program that defines the top level of their reasoning, by expanding its leaf components. Those are the so-called abducibles in logic programming, up to a given recursion limit. So we have a structured approach to LLM-generated logic programs, and we will also outline a few applications to clarify scientific, political decision processes. Let's start by describing the dual horn clauses, which are less popular than their well-known horn clause equivalents. So here's a contrast between definite horn clauses that are of the form P0 if P1 to Pn, with implication arrow pointing from the conjunction to the single head, that's the body, that's the head of the clause. Dual horn clauses will have the implication arrow pointing the other way from a given atom to a disjunction of its consequences. For integrity constraints, which are part of the horn and dual horn logic, we have that force is implied by P1, Pn, meaning that they cannot be true at the same time. And dually, it would be that true implies a disjunction, which means that at least one of these needs to be true. If one is true, well, we see that then the falsification would fail. Here, if one is false, the verification would fail. So they serve dual purposes. Now, dual horn clauses provide a constructive way to do falsification of a theory. A dual horn clause is an implication between a literal and disjunction, and in the case of the definite dual horn clauses, we have non-empty heads. Dual clauses with empty heads are called integrity constraints, as we have seen. We use Prolog-like syntax. We express a single arrow with this double arrow symbol, conjunction as in Prolog, and we express S implies false, representing a negated fact, the same way as S, if true, would represent a positive stated fact. And here is a small program in dual horn logic. If P implies that Q or R, and then Q implies R or S, given that R is false, then, and also S is false, it means Q will be false here. And then for this to be true, both of these need to be true, but Q is false. And by the way, R is also false. Therefore, none of this is true, which means that P implies actually false, which means we falsified P. P cannot be true. So we falsify P by backpropagating falsehood from its consequences. So the objective of dual horn programs is to describe constructively why something is not true. It works by falsifying the initiator goal, by backpropagating from its negative, undesirable, unwanted, harmful, impossible, and so on consequences. So we have here an instance of goal-directed forward reasoning. The goal being to bump into some consequences, well, many consequences that by backpropagation will falsify the goal we started from. LLMs are good at generating negative facts, as they are doing the same for positive facts, possibly a very large set of both, actually. We will show that together with horn clauses. Dual horn clauses will enable the LLMs reasoning with both horn and dual horn clauses in a program that puts them together, which we will see in a minute. So let's compare very quickly dual horn programs with constructive negation. While dual horn programs produce bindings of the form x equals t, constructive negation reduces a negated goal to binding of the form x different from t. So in that sense, it's, well, called constructive because it actually reduces negation as failure to bindings, differences, actually, not bindings, but the opposite of them. X cannot be t. So it kind of constructively reduces negation as failure to something simple, negation of an equality, basically. They tell us what X cannot be, information only useful if a generator provides candidates for what X could be. And that's usually part of a constraint solver. So we have recovered here a genuinely constructive mechanism to deal with inference about negative facts. What you can see here by telling what those bindings actually are rather than what they could not be, without tacitly reflecting failure of a proof procedure at object language level. That's what negation as failure does, right? If you cannot prove something, then you infer it's not the case. So we have another differentiator here. We have polynomial complexity for the propositional case, and this propositional case is interesting because LLMs actually are very good at generating logically connected statements, so they are propositional. We can force them not to be so, but we usually lose both precision and kind of convenience in using them if we force them to generate more complex horn or even general Prolog statements, which they can do. Like horn clauses, dual horn clauses retain polynomial complexity for satisfiability testing. So both of those are implied by Schaeffer's dichotomy theorem. They are basically both typical p-complete classes. So we can use efficient fixed point computations to find the unique minimal model for those propositional programs. And by contrast, negation as failure in the general case and its stable models-based elaborations, for instance, ASP, are NP-hard. And negation as failure, in fact, forces you to have the equivalent of disjunction in the head of a horn clause, which then brings in multiple stable models. That's the simplified story of what's happening, and which is not happening here. So let's look at putting them together, symmetric logic programs. The SymLP language combines horn clauses and dual horn clauses into Prolog. Some syntax notation, we mark with plus facts that are true, minus facts that are false. We use, as we mentioned, the implication symbol, left to right or right to left, to represent implications for horn and dual horn close head and bodies. We can consider minus p as a shortcut for p implies false, and plus p as a shortcut for p is implied by true. So we borrow from Prolog the usual notation for conjunction and disjunction. So we have a compilation scheme. That's very simple. We just compile the dual horn clause that we can see here into its dual, well, which is a horn clause that you can see here. Very simple. You just turn this into that and turn this into that. So successful proof in the later implements successful falsification in the former. So we get a compilation scheme from dual horn to horn programs with no runtime overhead. This is just a macro expansion in Prolog. Then given that dual horn clauses are transformed into equivalent horn clauses, the same SLD resolution applies to them if we want to run them in Prolog to find their answers and well, traces towards finding the answers, which is more interesting in the propositional case. Compilation ensures that backward reasoning on horn clauses mirrors forward reasoning on dual horn clauses. And it enables seamless integration in existing Prolog systems, and it preserves efficiency and logical correctness. So let's see a bit reasoning with a SymLP fragment. We have here a dual horn fragment, and here we have the horn fragment. So after we compile them, the dual horn lands in the module false, and the horn fragment lands in the module true. So now when we run them, of course, success here means that is basically false, and success here means that is true. So here the falsification process got turned into a goal, which was goal-driven forward reasoning, got turned into goal-driven backward reasoning as we know it in Prolog. So when we query those programs, in the module false we call P, it comes out as true, but that means that P is indeed falsifiable. querying through U here confirms that U is verifiable. SymLP uses deep LLM to provide this goal-driven recursive descent in an LLM's mind. So we have an app here. We encourage you to click on it. It's a SymPL Symplan app in this Streamlit app repository, and you can play with it and enter programs, and it's interactive. We'll see some examples of using it in a few minutes. So Deep LLM then replaces SLD resolutions close selections via unification by LLM-driven dynamic close head plus close body invention. So the LLM doesn't have the clauses as it progresses in generating new reasoning steps. It invents them. So dialogue units are sentences. The underlying logic is propositional. And the client-side management via the API of the LLM's memory uses a goal stack and a goal trace recording the steps of the current search path. So we need to keep the history of what happened. Like with any LLM-related prompt engineering, the previous steps memory needs to be managed. For natural language processing, we sometimes summarize it if it gets too big. In this case, it's a trace of what steps we took so far to get to the point where that new invention happens. Instead of variable bindings, answers are traces of justification steps, then explaining where they are derived from. When their depth limit is reached, the items on the goal stack are interpreted as abducibles, statements that can be hypothetically assumed and then checked against integrity constraints or refuted by oracles in a multi-agent framework or by humans in the loop. So let's take a look at a few examples now. Exploring a policy decision with SymLP. So we will explore the pros, and after that we will explore the cons for that. And this is actually the interface that the app that I mentioned the link of provides. So we enter a text of topic to explore or NATLOG program for verification or falsification task. So NATLOG is a simplified Prolog with a slightly lighter syntax, just in case someone doesn't know Prolog. That's digestible by just looking at it. So tariffs are good because tariffs allegedly add jobs and balance the budget. So now we want to support that, and our prompt engineering under the hood makes the LLM do its best to support that tariffs are good. Adding jobs means either domestic manufacturing incentives or export market expansion, balancing the budget also expands into this or that. Domestic manufacturing incentives, once you expanded it here, it further expands, as you see. Could bring tax reduction policies, infrastructure investment, workforce training programs, so reasonably creative positives that come out from this. And also export market expansion and so on. So this is how far we get with support arguments with tariffs are good, and that's because we set recursion level to 1, and well, even at level 1 there is more and then at the end, a model, the unique stable model, is generated as part of the application, and that can be seen there. Now let's look at the cons for the same. So the LLM is forced to go along what we said here. Tariffs are good because they are jobs and because tariffs balance the budget. So very positively inclined here. Now the prompt engineering forces the LLM to try to see that this is not that great, and then maybe falsify this and that, and then falsify that. So tariffs add jobs, unfortunately, means increased consumer prices, trade partner retaliation, supply chain disruptions, limited product variety, global trade tensions. So you would see innovation stagnation. So some of the things that are not that obvious coming from this positive statement that it was forced to go through, the tariffs are jobs. That looks very good, right, in theory. Tariffs balance budget, again, several of those things that are actually not that great, trade partner retaliation, supply chain disruptions. And this was made about 4 or 5 months ago, and we have seen the story, the real-time story in US, going very much along those lines, on the two sides, in fact. Generating the verifier and falsifier whole clause programs with NatLog. So as I said, NatLog is a simplified Prolog system. Here is a link to it. It has also an app of its own on the Streamlit repo, and it has the advantage that it is extremely easy to interface with the Python ecosystem because it is in Python. Not very slow, actually. It's reasonably fast for the few things that we ask it to do in terms of top-level logic reasoning, and of course the LLM, which is driven in the Python and relies on the Python ecosystem overall, would do the exploration via the verifier and the falsifier. So we guide it with NatLog code. We specify the limit. We define verify, which actually are defined in Python, and falsify. And then here is an example for buying an EV and avoiding an EV with the usual pros and cons, and then the Python definitions for verify and falsify here. Running the Explorer means triggering the LLMs, deep LLM programs exploration of the Prolog program, the invention of the Prolog program, driven by a verifier prompter or a falsifier prompter. And let's look at another example. Time is getting relatively short. We'll speed up a bit here. Exploring a theory with SimLLP. So the pros and the cons. The cons, the theory is that the universe is a computer simulation. And well, the pros are a bit weaker here, but anyway, we try to seed it by saying its K parameters are perfectly adjusted. That's why we are in it and happy. We can already emulate physics realistically in video games. So by expanding that, we get some of the positives for why we would live in a simulation. But the cons are more interesting here, except for some reasonably famous people who might still believe that that could be so. Well, the universe is a computer simulation. It goes along this line, but then it gets to falsifiable things, like if it's perfectly adjusted, and when there is no such thing as free will, diminished human agency, ethical responsibility is void. So that's the ethical part, but also we can already emulate physics realistically in video games. Well, that's diminished scientific inquiry, ethical responsibility crisis, existential meaning erosion, and so on. So you would see the pros and the cons for this one, and agree or disagree. Exploring an emerging technology with SimLP is another application, artificial general intelligence, and here we see also the pros for it, robotization, manufacturing, that's a good thing, right? Humans don't need to work, and the negatives of it as well. So among the negatives, you would see that, for instance, robotization has a consequence that we don't like: job displacement crisis, economic inequality surge, skill redundancy issue, workforce morale decline. So we see that there are positives and negatives for that, and again, that could be explored quite deep, and you get meaningful pro and cons elements that could help your decision process. So in conclusion, we have illustrated a novel approach combining logic programming with the knowledge encapsulated in large language models to rigorously guide exploration and reasoning tasks. So this hybrid methodology facilitates deeper understanding and clearer articulation of both supporting arguments and potential counter-arguments. So it's very useful for decision-making scenarios. Some future direction would be applications to medical, legal, and financial reasoning, some user-centric enhancements that leverage interactive editing and validation steps, so making the human in the loop a bit more active. And of course, for teaching, combining the use of simple horn and dual horn program can help with logical thinking and argumentation. And in this case, their simplicity actually, in both cases, seems like an advantage compared to more sophisticated, let's say, non-monotonic forms of reasoning and other logic programming formalisms that are more powerful, but also more complicated and possibly less intuitive when we want to develop at an early stage logical thinking and argumentation skills. Thank you very much.